All right, everybody. Hi, welcome to our Unit C Chapter 1 review. This is on electromagnetic fields, also gravitational fields as well. Here we go. So I'm going to mention which lesson we're reviewing, so you can go back and look for more details as needed. You could rewatch those lesson videos as well. Anyway, so here we go. So lesson 1 started off with field lines, and you looked at 3 types of fields. We looked at gravitational fields, electric fields, and magnetic fields. So when we're drawing field lines, though, we need to draw the direction of this field. So when we're looking at something like gravitational field lines, we are looking at things that are falling towards Earth. So our field lines are going to be showing the direction of the field, which is always going to be for gravity towards the Earth. Okay, so our test object, so what do we use to figure out which direction our field is? That's what a test object is. And anything with mass, anything with a mass. So in this example, you see an apple. And so the direction the apple would fall is towards the Earth. So gravitational field lines are always towards the Earth. When we're talking about electric fields, we are going to use a test object of a positive charge. So which way would a positive charge move when placed in the electric field? And positive charges always attract opposites. Right? So they always like opposites. So positive and negative are opposites. So our positive is going to move towards the negative and away from the positive. So this is showing you the direction of the field lines are always going to be drawn from away from positive and towards negative. If you only have one charge sitting there by itself, it's the same idea. So positive, the field lines are always going to move away from positive because our test object, our positive charge, will be repelled by another positive charge. When we're talking about magnetic fields, our test object to help us figure out which way the field lines move is a north end of a magnet. So which way is the north end of the magnet going to move? Opposites attract again. Got to remember that. Opposites attract. So north is going to be attracted to south, so it's going to move towards the south. So our field lines are always going to be drawn from north to south with a magnet. All right, so moving on already. Lesson 1.2, we looked at field strength, and we started off with gravitational field strength. There is your formula for gravitational field strength, little g. Always keep in mind that big G is a constant. It's in your data booklet. You should know where that is in your data booklet now. Your mass is always going to be in kilograms, so make sure if you're given any other units, you change them to kilograms. Same deal with the radius or the distance center to center of objects. You need to have that in meters, and you may be given numbers in kilometers. Make sure you can go and change that to meters, and to do that, you're going to multiply by 1,000. So some of the key things here too you need to know. What happens to the gravitational field strength if the mass increases? If your mass, which is on top of your, so it's a denominator in here, numerator, oh goodness. Anyway, it's on top of the fraction. If it gets larger, then your gravitational field strength is going to increase. They both increase. If the radius between the objects or the distance between those two objects increases, that's going to make this number down here increase quite a lot. So your gravitational field strength will reduce or decrease. The next formula we looked at is gravitational force. So this is where you would use that gravitational field strength that you calculated in that last question maybe, or it'll be given to you, and you pop that into your force equation, and then you have a mass that is in this field. So it's in this field, and it's feeling this gravitational field strength, so we want to find the force that it's feeling. All of these definitions for all of these different variables are in your data booklet, so just read it very carefully to make sure you're solving or finding the right ones. So here's an example from your textbook page 331, where you need to go and refer to your data table or your data booklet to find the formula that you're going to be using. So it's all in reading the question very carefully. So the moon has an average radius of 1.74. So you can see they've got a radius down here times 10 to the 3 kilometers. Now, we talked about this. Our radius, and you can look in the data booklet here, needs to be in meters, it says. So first thing these people this question is doing is taking those kilometers and changing them to meters by multiplying by 1,000. First thing they do. All right, and then there is a mass. The moon has a mass of 7.3 times 10 to the 22 kilograms. So we're writing down that variable as well. So important to write down what you have so you can figure out what you need. So, and the mass is in, let's just check our data booklet. It's in kilograms, so we're good to go. So we don't have to do anything to that one. Now, in question part A, we're trying to find the gravitational field strength. What is gravitational field strength? If you're not sure, look in your data booklet, and little g, you can see magnitude of gravitational field strength. That's what we're trying to find. Little g is what we don't know. So we're going to use our equation for little g, or gravitational field strength. Here, we're going to pop in all our values. So G, big G here is just a constant, again, from your data booklet, so you don't need to memorize anything here. You can see 6.67 times 10 to the negative 11. That's going into your formula, times by your mass from the question, and the meter distance, or R, from your question. Don't forget the little square. You need to square R. Okay. Do a few of these practice ones on your calculator. If you haven't done this yet, here's a perfect opportunity for you to pause the video and try this on your calculator. If you're not getting this answer exactly, then you're doing something wrong on your calculator. If you're not using your EE button or the EXP button to put in times 10, then you're probably going to be off by a decimal or two place. Okay, if you are typing times 10 to the hat, then you're probably going to be off by some decimals, so don't do that. All right, the next question on this in here is taking an astronaut has an astronaut has a new lightweight space suit of about 100 kilograms. That doesn't seem very light to me, and could be considered a test body for the gravitational field of the moon. Determine the force of gravity. Determine the force of gravity exerted by the astronaut on the moon's gravitational field. So we're going to take our moon's gravitational field that we just calculated in part A of the question, and we're going to use that. We know we're given a mass of 100 kilograms. That's our test mass. And so we're trying to find the force of gravity on that. All right, and if you're wondering, you're like, force of gravity, what is that? What is that? Oh, look, it's right there, force due to gravity. So again, everything is in your data booklet. You just need to know where to look and practice looking. So force of gravity, the formula is right here as well. And so it's force of gravity equals mass m times g, little g, which is the gravitational field strength. Plug in your values. Multiply, straightforward, and you get your answer of forces in newtons. If you're not sure what units, again, back to your data booklet. You can see your data booklet will tell you the units for every variable. All right, one thing you make sure you know, we did spend a lot of time on this because you did do a lab about this, but what's the effect of 1 over r squared on the gravitational field strength, right? You saw 1 over r squared for the gravitational field strength formula. So how does that affect field strength? So I love this diagram from the textbook, actually, page 333. You might want to just take a peek at it. It does a great job of explaining. So if you have the radius of Mercury and your gravitational field strength at just regular straight old R is 3.9 newtons per kilogram. If you double that radius, so now it's 2R, you can look and see what they're doing here to figure out what factor the gravitational field strength would change by. So 1 over r squared is 2 times larger than r. So they take that fraction, 1 over r squared, and put the 2 in for the r. So it's 1 over 2 squared now. 1 over 2 squared becomes 1 over a quarter, right? And multiply that by original gravitational field strength, and you get a reduced field strength by a quarter. So you're basically dividing by 4 of 0.90. There you go. Now what happens when you triple the distance away from the object, or 3r? And you can see you put that 3 in for the r, and it becomes 1 over 3 squared, 1 over 3 squared, 1 over 9. Multiply that by the original gravitational field strength, and you get a 0.4 newton per kilogram gravitational field. So it's decreasing by 9. So it's, remember, this is exponential relationship, a decrease relationship. All right, so same deal with electric field strength. Remember, it's pretty much the same formula as gravitational field strength, except, well, you're finding the electrical field strength, so it has a different constant or variable to represent it, capital E. And remember, these lines mean you're just taking the absolute value. So if it's negative, you'd turn it to a positive. You have a constant again, or your k, little k this time is your constant in your data booklet, 8.99 times 10 to the 9. Q is the charge, so instead of mass, we're talking about the charge on the object. And we still have radius squared, or distance center to center of the two charges down below. Okay. So again, this shape is our exponential decrease. It works exactly the same way for electric field strength as it does for gravitational field strength. There are going to, the field strength is going to be reduced a lot as the distance between the objects or charges increases. As same with gravitational field strength and gravitational force, we also have electric field strength and electric force. So you're going to be using your electric force equation as well. Now this is the one that wasn't in your data booklet. So if you haven't copied that down by now, make sure you get that in there too. So here is your E for your electric field strength, and Q is a little test charge, or a test charge you're going to be putting into that field to see what the force it would feel is. All right, so there's another great practice problem from your textbook that covers both electric field strength and force on page 336 of your textbook. I would suggest reviewing this carefully just to make sure that you can do both gravitational field strength and force, and electric field strength and force. Now, you did both of these kinds of questions in your assignment number 1 too, so that's a good place to go back and review. All right, lesson 1.3, motors and generators. Simple electric motors was the first topic we started with in this section. So we looked at motors and then we looked at generators. Now, what is a motor? A motor is going to take some kind of electrical energy, whether it's from a battery or gasoline burning, some kind of electrical energy, and turn it into mechanical energy. All right. So it's going to take this electrical energy from a battery or some kind of wire current and turn it into mechanical, which is the kind of energy that creates movement. Okay. Now, a motor consists of a few key components. The first off is you have to have a power source, whatever that might be, creating a current. You need to have your coils of wire, and you need to have those coils of wire inside a permanent magnet structure. As soon as you put a current through these wires, the wires between them become magnetized, which causes the wires to turn because of the permanent magnets on either side. They now want to repel and move away from or move towards the magnets that they attract to. All right, so as current flows through the coils, a magnetic field is generated. This is induced magnetic fields. Really important when we have electrons flowing, when they're moving. That's what current is, right? When we have a current, when they're flowing, then we get a magnetic field created. Always, always. A magnetic field is generated. And then this magnetic field is used to make this coil turn because we put these magnets here, permanent magnets, and they make the coils turn. And then we can connect this armature that these coils are on to some kind of blades, like to do a fan or blow whatever you're going to turn, wheels. All right, so generators are opposite to motors. So this is the opposite. Instead of putting in electrical energy is our output so that we can light a light bulb or whatever it might be. So we need to put mechanical energy in. Well, we could turn it, or we could use water or wind to turn this loop. The idea again is you have a loop of coils of wire, and if you turn them inside a magnetic field, then you create a current. So this is electrical induction again. So this is producing a current. So again, generators are opposite to motors. So a generator takes in mechanical energy and puts out electrical energy. A motor could then take that electrical energy and produce mechanical energy. So it's this nice kind of cycle, but they don't necessarily always work together. All right, lesson 1.4, moving on, types of circuits. Here we are going to get into quite a few more equations now. We've got the series circuit, which has just one loop. And your example was old Christmas lights. When one of these light bulbs goes out, they all go out. Whereas a parallel circuit, there's loops and multiple pathways for the current to flow. This is what you're going to find in your car, your home, or power bars. So if one light bulb is turned off or goes out, all the other ones keep working. So the electrons can just skip that path and go through the other paths. You need to know all these parts. You've used them all now, probably, and you've seen them all now a few times if you've been doing your practice questions. So you also need to understand that ammeters, to use an ammeter to measure current, right, it has to be in series. So it needs to be right in the main loop of the circuit, right? If you put an ammeter here, that ammeter will measure current, but it's only going to measure the current that goes through this resistor and that ammeter. So it's going to miss out on the current that goes through this part here. So if you want to make sure you get all the current for this whole circuit, you need to have the ammeter in before the current gets split between these two different pathways. Okay. So ammeters are put into circuits in series, and then voltmeters look like this, and they go on either side of a resistor. And so this is what a resistor looks like. Voltmeter could also be put on either side of a battery to measure the voltage. They could be put on either side of a light bulb to measure the voltage, but they need to be put in parallel. So you create a new circuit around the part of the circuit that you need, creating another path around the part of the circuit you're trying to measure. All right, a couple things when you put batteries in series, the voltage will add up. So you'll get a lot greater voltage, but they just don't last as long. But batteries in parallel, so you're still going to have this equal voltage. They're just going to equal each other out because this electron, doesn't matter which path it takes, it's only going to feel that voltage from one of the batteries. So your total voltage does not add up, but what it does is it lasts longer. All right, calculating resistance. Yes, this is good. I'm glad we're hitting this right now. So there was a slight error on the last on this slide. If you watch or use the notes from lesson 1. This is 1.4. Yes. So watch for this. So when we're looking for calculating total resistance of resistors in a circuit, if we're looking at series. So this is a series, so resistors in series. These resistors are just going to add up nicely. So all the resistance of each resistor is just going to add up and we get our total. Super straightforward, as long as they're in series. As soon as you have resistors in parallel circuits like this, that's when things change a bit. So we use this formula. 1 over the total resistance is equal to 1 over the resistor 1, 1 over resistor 2, and 1 over resistor 3. We put our resistance in, and instead of keeping them as fractions, we're going to change each to a decimal. So I'm going to take 1 divided by 4 is 0.25. If you're not sure what that is, pause and try that. 1 divided by 2, 0.5. 1 divided by 3, 0.3. Add all these up, and you get 0.92. Okay. I thought I changed the slide. I did not. Okay, this is what the problem. This is what the problem is. Okay, here we go. So you add all these up, and you don't get 0.92. You get 1.08. Can you make sure you do this on your calculator? Try this. 1.08. But that is not equal to our total resistance. It's equal to 1 over our total resistance. So we kind of have to flip both sides now. Okay, so we're going to divide both sides by 1, so we get just total resistance by itself. But then we have to divide 1.08 by 1. So we're going to have 1 over 1.08. And what does that equal? So 1 divided by 1.08 is where we get our 0.9, it's actually 93 ohms. And that is our actual answer to this question. That's the total resistance. So this is the trick. You change each of these fractions to decimals, add all the decimals up, and then your last step has to be 1 divided by this number to get just to our total resistance. I'm going to fix the slide so when you print off these notes, it's not looking like that. Alrighty, so there's a few more electricity formulas that you need to know here. There's Ohm's law, where you're looking at voltage, current, and resistance, and you have these triangles to help you out. If you want to use them, make sure you write down your rearranged formulas. You also looked at power, and there was 2 formulas for power, and this is power is the rate of doing work or transforming energy. It's measured in watts or joules per second. And here are our 2 equations. For power equals current times voltage, or power can equals current squared times resistance. It's going to depend what kind of information you have. If you have resistance and current, you're going to use this formula. If you have current and voltage, you'll use that formula to find power. So here again are both of those power equations rearranged. Make sure you have the rearrangements in your data booklet if you don't think you can rearrange them in your head. Alrighty, so some examples for power. Here are 2 examples from your textbook, again, page 388, on how you would use each of these different equations. If you read the question very carefully and write down what you have and what you're looking for, you'll be able to see why you're using the formula you're using. So you're using a simplified approach. A speaker can be treated as a device that offers 4.0 ohms of resistance, R, to the AC input signal, allowing only 2.0 amps of current, so that's our current, I, to flow. Calculate the power consumption by the speaker. So we're looking for power. So we know our resistance is 4 ohms. We know our current is 2 amps, and we're trying to find power. Why are they finding? Oh yeah, they're finding voltage. Okay, got it. Wait a second. Why aren't they using the other formula? I know why they aren't using the other power formula, because they were using this to show you how the power formula was going to be used. So I'm going to use the other power formula because all I have is resistance and current, and I want to find power. So I don't have enough to use that formula, but if I go over here, I've got current and I've got resistance. I can quickly directly find power. So I can pop in my current of 2, right? 2 squared times my resistance, which I have here, which is 4 ohms. So 2 squared is 4 times the 4 that's there. So 16 is my power, and power is in watts. All right, so what they did in this question was fine too. You could do this if you're not sure what to do. They found voltage first, and then because they had this power formula, they put voltage and the current in there like that to find the answer. Either way you do it, you get the 16 watts. But you can save yourself a bit of time if you know both of these power formulas. Choose the one that you have all the data for. Now, energy. When your question asks for energy, it could ask for energy in kilowatts, or it could ask for energy in joules. So make sure if your energy is being asked for in kilowatts, here's your energy formula. It's always the same formula, but you can put in this is the only time you can put in your units could be different for what you're putting in. So if you want your energy in kilowatt hours, you need to have your power in kilowatts and your time in hours. When you multiply them together, you get kilowatt hours. If you want your energy in joules, you need to have your power in watts and your time in seconds. So sometimes you can choose what you want, but you need to figure out what your question is asking for. So here's an example on page 390 of a question from the textbook. You might want to check out this. A kettle rated 1,000 watts operates for a total of 60 minutes in a typical week. Okay, so we know watts is our power, so we're going to write that down. And we've got 60 minutes as our time. Let's see what they want. First part of the question, determine the energies consumed in kilowatt hours. All right, I want energy and I want it in kilowatt hours. If I want it in kilowatt hours, then my power needs to be in kilowatts and my time needs to be in hours. So you're going to have to convert. So to go from watts to kilowatts, you need to divide by 1,000. Okay. If you're going from minutes to hours, you need to divide by 60. 1 hour. So they've done the unit conversions. Then you can take these two that you found. So your power, you're gonna plug it in, and your time, you're gonna plug it in here. And you multiply them together. 1 kilowatt times 1 hour gives you 1 kilowatt hour. That's the amount of energy. Now, in question 2, they're asking for, or in question B, determine the energy in joules. So if you want joules, you need to be putting in joules and joules per second, or watts. You need to have your power in watts, which is the same as joules per second, and you need to have your time in seconds. So they've gone and changed these minutes to seconds. So if it could be either in watts or joules per second, and the time has to be seconds, then when you multiply your power in watts times your time in seconds, you get the joules coming out. Oh, right. And then this last thing you're going to be looking at, this is the last one, is you can take that energy. Why do we want to know amount of energy? The amount of energy something is using on like an appliance, because then we can figure out what it's going to cost us. So if we know this is the amount of energy our appliance costs us, and here is our actual cost that we're being, our charge, our rate, I should say, our rate. So it's saying 7 cents per kilowatt hour. So we can multiply the 7 cents times our kilowatt hour to get our cost for that appliance to be used. Oh, right. Last thing is transformers. So we looked at step up transformers and step down transformers. You need to understand that step up increase the voltage, and in a step up, that means you're going to have more coils on the secondary side, on the output side, the side that you're sending to give the electricity to. A step down, the voltage is decreased, so you're going to have less coils on the secondary side. So it's going to step the voltage down. You have these 3 different formulas here for transformers. Make sure you've done your practice questions so you've been able to use all of these different equations. Doesn't matter which equation you use. Well, no, it matters. It just depends on what you're given in your question. Okay, so let's take a look at this example from page 401. You have a large neon sign powered by high voltage power supply. The power supply takes 240 volts input. Okay, so this is input is going to means primary. Whoa, that did not spell very well. But this is VP basically. Okay, so you've got VP, and then uses a transformer to increase the voltage to 12,000 volts. Okay, so this is getting increased. So this is your V secondary. It's pumping it up. Does the power supply use a step up or step down? Well, because it's increasing the voltage, it's going to be a step up. If the transformer has 125 turn wires on the primary coil, so turned wires is an N, number of turns, and it's NP, is 125. Determine the number of coils on the secondary, so we're trying to find NS. So we have voltage and we have turns. So we're going to find the formula that has volts and turns. This is the formula that we're going to be using for this calculation. You can see they've copied it out over here. What they've done is rearranged to find the formula for the coils like that before they put the number in, or you can just put your numbers in and do the cross multiplying like I did in the example question. Either way you're most comfortable with the math, you can do whichever way you prefer. The trick is making sure that you're putting in your values for the right variables. If you want to see the cross multiplying method, you can go back and watch that last lesson because I have an example in there of where I'm doing the cross multiplying. All right. And that is the end of the lesson. I would suggest going through the rest of this example and looking at a few more examples and practicing some of those practice questions from your textbook. That is the best way probably to study and make sure you've done some of these calculations before you hit the quiz. The last place you want to be testing your ability to do these calculations is on the quiz. So good luck.